Hi, and welcome to a lesson on number systems. The number systems we're going to talk about today are on the number line. This is a number line. Positive numbers are to the right of 0. And negative numbers are to the left of 0 on the number line. Let's look at that on our graph here. Let's see, the positive numbers are to the right. These are all positive numbers up to infinity. And negative numbers are to the left, all negative numbers down to infinity. Natural numbers are numbers that really exist in like nature. So it starts at 1 because the least you can have of something is 1. Keeps on going up, up, up to infinity again. Well, you can't really have infinity, but a very high number. Natural numbers, so it starts at 1. Whole numbers are the numbers that we say start at 0 and go all the way up 1, 2, 3, 4, all the way to infinity. So that would be whole numbers. Okay, great. Integers are all the negatives and positives together. It's like the whole number line is integers. So when you're drawing a number line, you're really drawing a graph of all integers. Great. Rational numbers. Rational numbers are numbers that can be written as A over B, where B is not 0. B cannot be 0 because you can't divide something into no parts. And A and B are integers. Great. A square root, like the square root of 64, is equal to 8 or is equal to negative 8 because 8 times 8 is 64, or negative times negative 8 is 64 also. Great. Irrational numbers are numbers that you can't really express, but we write them in math, like the square root of negative 1. There's no two numbers that multiply together to get negative 1. 2, that's a non-repeating 6 over 0. Because you can't divide something into no parts because something's going to be at least one part. Can't be written as A over B. That's irrational numbers. And what we call real numbers are all rationals and irrationals. Great. Let's look at some examples of how we classify. Okay, classify real numbers. 1/3. That can be written as A over B, and let's see, A is equal to 1, and B is equal to 3, and these are integers. And B is not 0. So we would say this is a rational number. Great. The square root of 144, what multiplies by itself to get 144? It's 12 times 12 makes 144. For the square root is 12. So that is a natural number. It's a number that really exists in nature. It's an integer. It's also a whole number, and it is, of course, a rational number also. Okay, don't get fooled on this next one. The negative sign is outside the square root sign, so it might be a rational number, but let's see. That's approximately 3.049501. It goes on and on. It doesn't repeat. Since it doesn't repeat, we never can really define it. So that is an irrational number. Okay, let's look at something called closure property. Closure property is when you use an operation, that would mean, what I mean is plus, minus, divide, or multiply, with a set of numbers, the answer is part of the set. So, for example, if I have a whole number and I multiply it by a whole number, am I going to end up with a whole number? If so, that would be a closure. in that set of numbers. For example, if I add integers, gets another integer. So that's closure. So let's think of whole numbers and times. So when I multiply a whole number, am I going to get a whole number? Let's see here. Let's do some tests with some whole numbers. Let's try 5 and 6. 5 times 6 is 30. That's a whole number. That works. 7 times 3. 7 times 3 is 21. That's a whole number. It works. Let's pick another whole number. 0 times 5. Multiply them. That's 0. That's a whole number. Since there's no counterexample here, can't find one. I can't think of another counterexample. So it is a closed set. Whole numbers is a closed set for times. Well, let's think of whole numbers and divide. Is it a closed set for divide? Let's test. Okay, let's test 6 divided by 1. That's 6. That works. That's a whole number. Let's do 20 divided by 5. Let's see. That's 4. Great. Let's try 16 divided by 0. Oh, that's an irrational number. Since that's an irrational number, that is a counterexample. So since we have a counterexample, this is not a closed set for whole numbers and division. Great. Now let's look at some examples of graphing real numbers. So let's see. This would be -3. This is 1 2/3. So let's see. -1/3 is a little bit past 0. It doesn't go quite to -1. This -3 is down here. Great. -2/3 is a little bit, no, that's +2/3, so that's not quite to 1 yet. And 1 2/3, that's right there. 1 2/3, or 5/3. Okay, number 2 says y is less than or equal to 4. So I have to graph 4. It includes 4, so I'm going to shade in that circle. And it's all numbers less than, so I'm going to shade all the way down in that direction. It's all numbers down there, starting at 4, including 4. Okay, x is greater than 1.3, but it doesn't include 1.3, so I'm going to do an open circle at 1.3, and it's greater than, all numbers greater than that. Great. Now let's look at some examples of finding square roots. Okay, this would be square root of -64 over -69. What's the square root of 64? 1 multiplies, that would be 8. Multiplies, that's 13, so it's -8 over 13. Great. So it's -8 over 13 is the answer, because it can't be simplified. Okay, this would be the square root of 9 over the square root of 25. Well, let's see, what's the square root of 9? Square root of 9 is 3, square root of 25 is 5, so that's 3/5. 3/5 is the answer. Okay, let's see, square root of 225 and the square root of 900. That's square root of 225 is what? That's 15, and 900 is 30, because it's 30 times 30, or 3 times 3 is 9. But that can be simplified, so I write it horizontally. What divides into that? Let's see. I know 5 divides into it, so let's try 5. And that's 3 and 10. I mean, 6. I know 3 divides into these two, so I can divide again. That's 1 and 2. So that answer is 1/2. Great. Let's look at some examples where we compare real numbers. So here I have the square root of 20. So what makes the square root of 20? Well, that's between, let's see, square root of 20 is between the square root of 16, which is a perfect square, and the square root of 25, because the square root of 16 is 4 and 5. So I know that number is between 4 and 5. So let's think about it. 4 and 5 and 3. Well, any number between 4 and 5 is greater than 3. So the square root of 20 is greater than 3. Okay, let's do this again. The square root of 42. Okay, so let's see. Let's think about square root of 42. That's between the square root of 36 and the square root of 49. So that would be 6 and 7. So that's between, the answer is between 6 and 7 for the square root of 42. And that would be greater than 4.3. So 4.3 is less than the square root of 42. Let's try it with the square root of 39. The square root of 39 is between the square root of 36 and the square root of 49. So let's see here. That would be 6 and 7. Well, since 6 and 7, any number between 6 and 7 is greater than 5.2, the answer is greater than. Great. Okay, let's look at some numbers in number line. We're going to graph them from least to greatest, or order them, but I'm going to graph them. Let's see the square root. That would be -3. That'd be 5, just making it easier for myself. That'd be -2, and that would be 1. So let's graph. Let's see, 3.4. So it's a little bit past 3. So 3.4 repeating is right there. -3. Let's see, that would be -3. So I'm going to write negative square root of 9 right there, because that is -3. See, 5. Going to go up 1, 2, 3, 4. Okay, we'll have another dot there. So that's 5. Then we have -2. So let's see, -2 will be there. So I'm going to write -64 over 32. And of course, 0 is just 0. And 8 over 8 is 1. 8 over 8 is, yeah, right there. Now, if I write it from left to right, I've ordered them from least to greatest. Square root of 9. Square root of 64 over 32, 0, 8 over 8, 3.4 repeating, and 10 over 2. Great. Thank you for joining us for our lesson on number systems. Now go get your homework done.